Thanks for the applause. We'll see at the end. That's the test, whether we get an applause. Thank you, Jose, for the introduction. And thank you for not mentioning all the other things I flunked out of. I did know Stanley Jaki on quite a number of occasions. He came to the Pontifical Academy of Sciences many times when we were both members. And I invited him on many occasions to come after the meetings there to the Vatican Observatory, which is about 20 miles south of Rome at Castel Gandolfo, the Pope's summer residence. And he often accepted that invitation. He would come and spend several days there, researching in the library, enjoying the countryside, and we had many conversations, always exuberant conversations for any of you who know Stanley Jaki. Okay? They say if you have, I'm a Jesuit, if you have two Jesuits together discussing one topic, you'll have 4 different opinions. If you have two Jesuits discussing 2 topics, you'll have 16 different opinions. In my discussions with Stanley Jaki, the number of opinions, we lost the exponents. They just went up in space. They were always stimulating conversation. So I'm very honored tonight to be the second lecture in this series. Well, let's get on with it. My title is posted here. And while it sounds kind of fanciful, by the way, I'm not going to dance. That would make you all cry. But I am going to talk about the dance of the fertile universe and chance and destiny. There are 3 fundamental ideas that run throughout my talk, okay? Fertile universe, chance, and destiny. And while I'm not going to define them, I don't think ever I'm going to talk around so we get ideas about what I mean. Did we, the universe and everything in it, including ourselves, come about by chance or necessity? Destiny, same word. What's the answer? It's a very important question to have an answer to, because it immediately implies a religious question. A religious question is implied right away, because it was by chance, pure chance, and it could have been that way. Actually, from science, as I'll try and talk to you about this evening, it's not sheerly by chance. But if it were by chance, who needs God? It just happened. But if it were necessitated, if it were destined, who did it? So the God question is embedded or implied, let's say, in what is a scientific question. So the scientific question is, did the universe and ourselves and everything in it come about by chance or necessity? By fertile universe, I mean essentially 2 scientific facts. That the universe is 13.7 billion years old. A billion is 1 with 9 zeros behind it. Okay? And it contains 10,000 billion stars. That's 1 with 22 zeros behind it, stars. We know that. They're scientific facts. Oh, give or take, here, give or take a few million. Give or take a few million here, and I don't care. How do we know these 2 facts? Give me a few seconds. From the Big Bang, which since the universe is 13.7 billion years old, the universe has been expanding. We have solid scientific observations that show this, both the measurement of galaxy velocities, the number of light elements in the universe, the cosmic background radiation. There are many independent scientific investigations that assure us the universe began in a Big Bang. It's been expanding, and this is a little pie slice of this big expanding universe. We are here at 13.7 billion years since the Big Bang. This is where we are in the universe. And we look back as far as we can to see the early universe. And I just learned this past week that with Hubble's telescope, we've looked back to 13.5 billion years, light years away, that is. So within a half a billion years since the Big Bang. Well, what do we see? With big telescopes like Hubble and those on the ground, we look back and we take a photograph of this early universe, at the beginning of the universe. And what do we see? That's what we see. And you say, well, what are you so excited about? They're just little dots of light. Well, these little dots of light, except for this here and that there, and there may be 5 stars on here, each of these dots of light is a galaxy that contains of the order of 100 billion stars. And if you don't believe me, let's sample a few. There's an irregular galaxy that contains about half the number of stars of our galaxy. There is an elliptical galaxy that contains of the order of 10 times the number of stars in our galaxy. And by the way, just by the way, it's eating up a baby galaxy. That's why it became a giant elliptical galaxy. We call it galactic cannibalism. And then down here is a spiral galaxy like our own. If you sampled all of these, you find they're all galaxies that contain of the order of 100 billion stars each. Now, this photograph was taken by Hubble of a piece of the sky that's about 1/20th the thickness of my index finger, because it wanted to look through nearby objects, and that's why you don't see many stars, to very distant objects. If I wanted to see the Empire State Building, whatever direction it's in, I'd take a very narrow view through this room so I didn't see your heads, so I could see very distant. And that's what Hubble did. Well, if this one photograph contains all these galaxies, we can do statistics around the whole universe, and that's how we come up with 10,000 billion galaxies, plus or minus a few million. So that's how we know that all of these stars exist in the universe. This is the Andromeda Galaxy. It's a sister galaxy to our own. It measures 100,000 light years across. It contains, as I said, 100 billion light years, 100 billion stars. I said 100,000 light years across, and before I said that we had seen back 13.5 billion light years. What is a light year? It sounds like a measure of time. It's not. It's a measure of distance. It's the distance light travels in a year going at the velocity of light. So it's a very large distance. But what it also means is we never see anything as it is. If I'm down here and my mother-in-law is up there, I don't have one, so I can say that, and I say, Mom, how are you feeling? 200,000 years later, if light traveled, if my voice traveled at the speed of light, which it doesn't, but let's forget that. 200,000 years later, my mother-in-law would say, I'm not feeling so well, my knees hurt, I can't. As we look out in space, we're looking back in time. So I don't see these young folks in the front row here as they are now, but as they were a millisecond ago. And the people coming in at the back there as they were a millisecond ago. And the sun, when it sets, I see it setting, but it set 8 minutes ago, because light had to travel 8 minutes from the sun to my house. That's a very important fact as we go along, that we never see the universe as it is, but as it was. This galaxy is very similar to our galaxy. How do we know the structure of our galaxy? Because we can't get outside it to photograph it. We feel around with large telescopes in our galaxy. We compare what we see to other galaxies, and we reconstruct the nature of our galaxy, and there it is. It's a spiral galaxy. The young stars are born in these spiral arms. The older stars are concentrated in the inner parts here. If we could view our galaxy not from above, but from an edge, it's a very flattened system. It's about 100 times longer than it is thick. And this next slide attempts to show that. Here is the center of the galaxy. The sun, and we, of course, are 28,000 light years, or 2/3 of the distance out from the center of our galaxy. And we're looking along, trying to reconstruct the nature of our galaxy. When we look along, as I just said, what do we see along the tabletop of our galaxy? Because we are embedded in the gook, so to speak, in our tabletop. This is what we see. This is a little piece of the previous slide taking an optical light. So this is a real photograph of the plane of our galaxy. What I want to concentrate on is not all the stars. There's so many here that it looks like a cloud, but that's because we can't resolve the individual star. What I'm interested in are these dark areas. Look at that incandescent gas in that dark area. The reason I'm interested in that is because that's where stars are being born. There's a little piece of the previous slide. It's called a dark cloud in our galaxy. It's kind of marvelous. It's called the North American Nebula for obvious reasons. There are the Gulf states, Georgia, Alabama, Mississippi, however they go, Yucatan Peninsula, Gulf of Mexico, Florida here, a little fogged over, but it has been since the elections in 2000. We're not doing a whole lot better, guys. Why are there so few stars here and so many stars in the Gulf states? There are not few stars here. What you see is not what you get. There are thousands, if not millions, of stars embedded in this gas where they have just been born, and we only see them when we penetrate that gas with infrared light. Here is a picture of the Orion Nebula. The center of that nebula is a place where stars are being formed. Here is a Hubble Space Telescope blown up view. Notice that, how pretty it is, right? But we scientists, oh, pretty fine, but what does it mean? And we know, why is the red gas concentrated here and the blue gas out there? Because the hottest, most massive, energetic stars have already been born in this gas. They're radiating the gas, it's absorbing that radiation and re-radiating it in the H-alpha line of hydrogen. So for you scientists, that's in the red region of the spectrum. This is blue because it's too far from the energetic star-forming region, so it's not absorbing the light and re-radiating it, it's reflecting it. And it's reflecting it in the same way that the Earth's atmosphere reflects sunlight, and that's why the Earth's atmosphere is blue. The Earth's sky is blue. Here is a beautiful view of the Orion Nebula with this incandescent cloud. Look at the red, the blue. This is a star-forming region. It's what we can justly call a stellar womb. How are stars born? In one of those clouds, the cloud begins to break up, do an interplay of gravity and magnetic fields, and these pieces begin to collapse. So there's a piece, there's a piece. This cloud here will form about 100 stars, a cluster of stars. And as the gas collapses, it heats up. Ordinary laws of physics. But in this case, it's several times the mass of the sun, so it raises the interior to millions of degrees and turns on a thermonuclear furnace. Now that sounds like a big physics idea. It's very simple. At that high temperature, hydrogen begins to fuse into helium. And after the temperature raises even higher by a further collapse, it'll convert helium into carbon. carbon into oxygen, silicon, nitrogen, all the way up to iron. Thermonuclear fusion converts in the interior of a star the lighter elements, hydrogen, helium, into the heavier elements. And that's what a star is. It's a thermonuclear furnace. Here is another example of a cloud breaking up to form a cluster of stars. Look how it's breaking up the blue gases out here because it's not close enough to the star-forming region. What is this? Or this? This and this are dead stars. In this case, they're white dwarfs. The sun will become this when it eventually dies. At the end, a star is desperately trying to raise the temperature so it can convert the next heaviest elements, because the temperature always has to be higher as you go up the periodic table of elements for fusion to take place. But there comes a time when the mass is not great enough to raise the temperature high enough to start the fusion process, and so the star has no energy source. So it collapses due to gravity a final time, and there's a rebound, okay, and it throws off a smoke ring to the universe. What is this? This star is identically that star. You don't do what astronomers do. See these two, these three here, those three there. This star is identically that star. In 5 days, this star increased its energy output by millions of times. It's what we call a supernova explosion. And after a few 100 million years, it will look like this. Look at this supernova explosion. It's a chaotic death, not like that peaceful smoke rings, because this star, when it died, had 5 to 10 times the mass of the sun. So it died in that kind of agonizing death. And again, in a few 100 million years more, it will look like, come on, this. Namely, that gas will disperse into the universe. This is a supernova remnant. Now, why am I talking about the birth and death of stars? Because from this gas here, left over from the death of a previous generation of stars, another generation of stars will be born. But with each generation of stars, the gas out of which they're born has many heavier elements. The universe, the gas in the universe to form stars, is getting more and more carbon-based, silicon-based. The sun is a third-generation star. We know that by measuring its spectrum, how many heavier elements it has in it, etc. The sun is a third-generation star, and if it were not, you and I would not be here. That's a scientific fact. We had to have 3 generations of stars to make the chemistry to make life. And we needed 3 generations to get enough carbon, nitrogen, to make the first life forms. We are born of stardust. That's a scientific fact. I have a professor friend at the University of Arizona who says we're born of thermonuclear waste. Well, I prefer to call it stardust. Okay, let's move on. Stars are born and stars die. Around one star, this happened. The material left over from the formation of the sun and from other stars had to form in a disk to conserve angular momentum. When it did, it was denser, so it collided, and by what we call the snowball effect, it built up planetesimals and a planetary system until we finally got this, the planets we know. And finally got this. Now, from what I've said, it's obvious. This is a grain of sand in a vast universe. It's one planet, okay, of 8 planets around one star, of 100 billion stars in our own galaxy that sits out towards 2/3 from the center, a universe of 100 billion galaxies, 10,000 billion stars. Okay? So I can justly call it a grain of sand, right? But it's very precious. And for many reasons, it's precious. One of them being the following, that through modern science, we developed the capacity to put the universe in our heads. And that's a marvelous achievement. Not even scientists really accept what a great achievement that is. I mean, I can tell you the mass of this galaxy. I can tell you how fast it's rotating. I can tell you what percentage of young stars are in that galaxy, what percentage of older stars, because I can use the laws of physics, chemistry, biology, all of modern science to study that galaxy by, in a way, putting it in my head. And of course, when we do that, we typically get more questions than we get answers. So let's approach at least one of the questions. I'm going to pass over this. This is to return to our galaxy. See, you sometimes may think these scientists are very fanciful. They draw all these diagrams and all. This is a picture of our galaxy, the tabletop of our galaxy, taken above our observatory in Arizona. Here is Tucson, and here is Phoenix. That's the only light we have in the sky here. So it's a perfect place for being able to study the structure of our galaxy. I've talked about the age of the universe, and although I'm only 158 years old, trying to rival Moses, I don't know what 14 billion means. I can't get an idea of it. So what we do is what mathematicians do all the time, scale down, make out that the universe, which is 13.7 billion, is 1 Earth year old. And of course what you see is what you see here. It began on 1 January. It's interesting that it took just a little over half the life of the universe for the Earth to come to be. A little over 6 months, 6.5, 7 months. But once the Earth came to be, it only took a couple weeks for the first life to come to be. That's an interesting fact. I don't know what to make of it quite, because you got to be careful as a scientist. Does that mean it's easy to make life? It came so fast. Once we got the Earth, solid crust, atmosphere, we got life, so it's easy to make it. Will you try and make it? We do not know how life began on the Earth. So drawing a conclusion from this to say that life must be very, very abundant in the universe, because look how easy it is to make, is not a real scientific way of thinking, frankly. The most interesting, well, the dinosaurs had the good fortune to be born on Christmas Day, but they were only around 5 days. But look at the last day of the year. This is coming up to now. Okay? Midnight is now. Jesus Christ was born 2 seconds ago. Galileo a second ago, so modern science has been around for a second. I'm trying to understand a universe that's a year old, and I've been at it for 1 second. So if I don't know everything, if we scientists pretend to know everything, we don't. It's a very young science. Science is very young in terms of the total age of the universe. First human beings came to be 2 minutes ago. It makes you stop and think about, are we really special in this universe? Let's review what we know. The universe, as time went on, up until now, 13.7 billion years, has been getting bigger. Distances have been getting bigger. And in this expanding universe, these various events happen. Why did it take 12 billion years, almost 2/3 of the age of the universe, to make life? Well, we know one reason. It took 3 generations of stars. And the sun is a third generation star. And like human beings, generations overlap. We have grandchildren, parents, grandparents, all living in the same city or so. So if you take 3 generations of stars and overlap them, 12 billion is just about right. The sun is 4.5 to 5 billion years old. What I want to ask now is, how did we come to be after the first microscopic life came to be? And I'm not an evolutionary biologist. I'm stepping outside my field. But I talk to my friends, and I feel I have to talk about it. From my knowledge of the universe as a whole, I want to know how we came to be in this expanding, fertile universe. And so I'm going to make an attempt at it. First of all, if we plot 2 of the most simple things you can measure about any physical thing, that is, how big it is, R. So I'm 5'10". Okay. How much mass it has, or to talk loosely, how much does it weigh? So 2 of the most fundamental things you can measure and plot them, this is what you get. All life forms fit into this general trend. Is that a proof that life came out of the universe the way everything else? I don't propose it as a proof, but it sure makes me curious. I want to know why I am drawn from this plot to examine how did life come to be amidst all these things that have come to be in this universe. That's how it came to be. Through what we call neo-Darwinian evolution. That is, first primitive life form. The nature of evolution is that life forms evolve because they're mutations, and we'll talk about that in a moment. An organism changes. That organism, to survive, go on into the future, has to adapt to an ecology that is changing, an environment that is constantly changing. So it's a very dynamic process, an interplay between an organism surviving into the future as the environment in which it's surviving is also changing. Why does it move forward to ever more complex organisms until we come to the human brain? It's the nature of the universe. There's a little bit of chemistry. I don't know what these chemicals are. I don't know enough chemistry. But what I do know is that H, C, N, and O repeat themselves. Time and hydrogen, carbon, oxygen, and nitrogen, the fundamental constituents of life forms, repeat themselves in ever more complex organisms. If you give this process 12 billion years, and then another 2 billion years, after 12 billion, you're going to have life. And after 14 billion, you're going to have us. Because that's the way chemistry works. It builds up ever more complex chemicals until we get the human brain. Oh, you say, but chemicals break down. There's decombination. Well, of course there is. But obviously, combination won out over decombination because we're here. Complexity won out in the end through chemistry. So now, if what I've said is true, or even partially true, there's some issues to talk about. Well, first of all, this gives a little more of where the origins of evolution is. It's in genetic mutations. And I'm sure you all know that the DNA, these strands unwind, and then they link up with another DNA that's unwinded, okay? And they have to link up with these letters in this way. These are the 4 fundamental bases, but sometimes they don't do it exactly. And that's what we call a genetic mutation. The problem with this for scientists is we can't put any time on this. They're completely random, as best we know. They just happen. Carbon dating is very exact because radiometry is very exact, because that's the way isotopes decay in a very strict timeline. But genetic mutations don't do that. But they do happen, and they're happening all the time, and you can read this as well as I can, okay? Once we get genetic mutations, we're building up new organisms eventually that have to adapt to their environment, and we have the evolutionary process going on. You know, I often ask myself, should I show this or shouldn't it? But I always wind up showing it. And the reason I do is because I'm sure there's some of you out there who are going to say, oh, that's great, but that's just a theory, this evolution. As the American word theory, I don't like to use. I like to say best scientific explanation to date. Because whenever I say theory, people say, it's just a theory. You know, I was in the shower and, you know, got out of the shower, I'm toweling down, I look out the window, I see these frogs jumping. I say, my goodness. A couple of days ago, I was watching the Summer Olympics on TV, and I saw these guys and gals jumping over these hurdles. We came from frogs. Well, we do better than that. And this is one of the betters that we do. This is very easy to explain. You have to admit that these organisms get more complicated. That is, that the human being is a little more complicated than a moth or a turtle. I assume you will accept that. We're more complex, chemically speaking. The number of mutations that we just talked about is this number here. The identical molecule, it's called cytochrome C, identical in all of these organisms. It's the same chemistry, but it went through different number of mutations. And to get the number of mutations for any higher organism, you have to add up all these branches. That's the way it's applied. So it's obvious that the more complex the organism, the more mutations that have taken place. So my conclusion is that these mutations have driven a process whereby we get more complicated organisms from less complicated organisms. Do you have a better explanation? Like to hear it? What you can justly say, you were lucky. You've got the right chemistry that led you to this conclusion. We've done this for thousands of identical molecules in all of these organisms, thousands. And we come up with the same conclusion. So the best scientific explanation is just what I said, neo-Darwinian evolution. Genetic mutations lead to adaptation of organisms to their environment, which is also changing all. Well, now I come to my own. I have to say something about chance. I think you understand what I mean by fertile. A very old universe, relatively speaking, where stars are pouring out all this chemistry. So we have this very fertile soup out of which we can build up complex organisms. The universe is fertile. In that fertile universe, mechanisms are happening to build up more complex organisms. But those mechanisms are a combination of both chance and necessity. What do I mean? Two atoms of hydrogen in the early universe meet one another. They have to make a hydrogen molecule. That's the nature of chemistry. They have no choice. But they don't at this place in time because the pressure and temperature conditions are not correct for that combination to take place. So those two atoms wander throughout the universe. They meet trillions of times. There are trillions of atoms constantly being replenished. What's to surprise us if a few million, a few billion times they make a hydrogen molecule? By chance, because we had to have the correct conditions, which we didn't always have, So there's a probability that it will happen. There's a probability it won't happen. And we know around certain stars the probability is higher than around other stars because the temperature and pressure conditions are different. So it's not just hand waving like I'm doing now. It is a real statistical study of how probable is it that we'll get a hydrogen molecule. We get two hydrogen molecules. They need an oxygen. They have to make water. But they don't at this time and place. They're at. So we get some water. It needs some carbon. It has to make up methane eventually. I forget how these chemicals go. But do you see the point? We're going through a very, very old universe, okay, where both chance and necessary processes are dancing together, building up more complex organisms. So that's the nature of the universe that I wanted to share with you. It's fertile in their chance and necessary processes, building up ever more complex organisms until we came to be. So, to conclude, this is a tree of the universe, not of life, of the universe. Everything that ever happened. The first galaxies, the first stars, my grandmother's birth, my toenails, whatever happened in the universe, including all those processes that failed, that never moved forward with more complex organisms. The two atoms that never made a hydrogen molecule, et cetera, et cetera. And that happened. Those failures happened. That's the nature of the universe. But obviously they didn't win out because we're here, those failed processes. But we want to clean this up because everything, all the failed processes, the dead leaves and dead branches are still here. Let's blow a quiet breeze through this. And what do we see? We inevitably see something like this. I use two phrases, inevitably, because I can't say necessarily. Because if I did say necessarily, I'd contradict everything I just said. And though I've done that on more than one occasion, I prefer not to. Something like, because the processes that are probable at a certain time could have kept the probability lower, etc., and we could be slightly different than we are. We could have arms that come off our belly buttons and our backs in this, and it would look strange, except we'd all look that way. I insist, I spent enough time in Italy, is if you develop the power of speech, you had to develop hands. There's no way. So there are certain things that had to be in combination, had to happen. However, it could be slightly different. I have to be fair and say that this tree I made up in order to make a point. Namely, we human beings are at the top. And it looks like, well, it looks like somebody did it, designed it, right? I mean, how could this ever? Well, the reason we're at the top is we don't know what else to put at the top. The human being is the most complex mechanism we know. But you do know that it's not a tree of life, it's a bush of life. So it's even more complicated than I presented it. And we are up here in this right-hand corner among the animals. But life is very abundant. It has this various branching from three fundamental branches. Well, my question is, did God do it? And I want to go back to this, because it presents the temptation, I call it. Did God do it? Well, I don't know. As a scientist, I have no way of knowing. All I know is this from my science, and I can explain this. But did God do it is beyond my scientific ability to know. Because if God did it, then the God who did it is more than my possibilities of knowing him through pure reason, beyond science, in other words. So to answer the question, did God do it? Well, of course God did it. But I don't know that from my science. I know that from religious faith. And we could talk for hours about what religious faith is, but at least let's say a word to conclude. So you know why I pose this question, and why I try to answer it, and why I come up from science, I don't know about God. So the question remains for science. But I'm more than a scientist. So if I believe that God created the universe as science sees it, science also tells me about God. If I believe, it's a big if. Why am I not permitted, as a religious believer who believe God created the universe, to say, I know this universe is this way from my science? Can't I ask the question, the God I believe created it, what kind of God is that God? And of course the answer is a magnificent God. A God did not make a washing machine. He did not make a car, store up parts, make sure you got enough gas. God made a universe that's very dynamic. It's not all prepackaged, predetermined. Its future is not completely settled. Their probability and necessity are still building up complex organisms in this fertile universe. Does that mean God is not omnipotent? Does that mean that God doesn't know everything? Well, we had a little discussion earlier today. You theologians are going to have to re-look from what we scientists know at what we mean by omniscience and omnipotence. What do we mean by that? From the nature of the universe that God created. And while they're not easy questions to answer, I think they're surely interesting ones for the interaction of science and religion. So for purposes of discussion, these are the points that I would make. And while I haven't talked, God is not an engineer who designed the universe. That belittles God, and it belittles science, to think that God is an engineer who designed the universe. God is a parent. The universe is a child that God is nurturing. But I'm babbling. What are you going to do? Whenever we talk about God, as the theologians, we always are babbling. But we have to talk about God. Why don't we use the best of our scientific knowledge to begin to talk about God, even if it's only babbling? Thank you very much for listening. That's it.